Hello again, everyone. Thanks for attending Analog Devices JESD204B webinar series. Again, my name is Del Jones, and I'm a staff applications engineer for ADI's high-speed converter products. Here's the schedule for the webinar series. We did the JESD204B transport layer last week. Today we'll be talking about the data link layer, and in the next 2 weeks we'll discuss the physical layer and associated topics, and then deterministic latency and multi-chip synchronization. Again, we won't necessarily cover every detail of the spec during these sessions, but we should cover most of the relevant aspects while discussing some of the implementation choices we've made in our converter products, and also how they would be used in the end application. So let's get started on the data link layer. So as part of the JESD204B data link layer discussion today, we'll define some terms that are used in association with the link layer, and then take a closer look at the functional blocks in the link layer. We will spend most of our time discussing the details of the link synchronization process that is carried out by the link layer. We will also discuss error monitoring and test patterns used for testing the link layer. Here are some of the terms we will be using today. Both CGS and ILAS are part of the link establishment process. Code group synchronization is the first part of this process, where code group alignment is established. The initial lane alignment sequence occurs after CGS and uses special alignment characters to achieve frame and multi-frame synchronization and to align all of the lanes in the link. Character replacement is a method used to monitor frame and multi-frame alignment. Scrambling is a process applied to the data being transmitted across the link so that spurious spectral lines are reduced. The sync signal is an LVDS signal generated on the JESD204 receiver and is used to communicate back to the transmitter. Subclass 1 is a JESD204B classification for implementing deterministic latency. Although we will be referencing subclasses today, most of the details will be covered in our last session of the webinar on deterministic latency. You'll recognize this block diagram from last week, but it's the high-level block diagram of the JESD204B transmitter that's incorporated on an ADC. The data link layer brings in framed octets from the transport layer. Depending on the sample size and system requirements, the framed octets will include control and tail bits along with ADC sample data. As mentioned during our discussion on the transport layer, the data, as it passes through the data link layer, is parallel. The width of the parallel data bus depends on the architecture of the framer. For a dual byte framer, the bus width at the input to the data link layer is 16 bits, and for a quad byte framer, the width is 32. This data first passes through the scrambler, where it may or may not be scrambled, depending on the end user's requirement. This option is controlled via SPI-bit. Alignment characters are generated according to the frame and multi-frame clocks and are transmitted in the place of sample data as part of the synchronization process. Some control characters are also used during the transmission of sample data as part of a process called character replacement, which is used for monitoring alignment on the receiver end. This will be covered in detail on later slides. The data link layer on the JESD204 transmitter also handles requests for realignment via the sync input, as well as inserting the JESD204 configuration parameters as part of the ILA sequence. The link layer is also responsible for encoding the 8-bit octets into 10-bit code groups. And lastly, prior to sending the code groups to the serializer, a Crossbar function is added. We will discuss each of these blocks in more detail on the following slides. All right, on the DAC side, we have a similar block diagram. This one's for the JESD204B receiver incorporated on the DAC. The function of the data link layer on the receiver is the inverse of the transmitter functions. The link layer brings in the deserialized 10-bit code groups, performs 10-bit to 8-bit decoding, performs descrambling if necessary, and sends the framed octets to the transport layer. The link layer of the JESD204 receiver aligns the data to its sysref-aligned frame and multi-frame boundaries, and also performs lane alignment. During sample data transmission, it monitors lane alignment and reports any associated errors. The crossbar function is also included. So let's take a little closer look at each of these functional blocks in the data link layer. The JESD204B spec defines the scrambling polynomial, type, and bit order in section 5.2. The scrambler is self-synchronizing, and the polynomial is 1 plus x to the 14th plus x to the 15th, and is depicted in the diagram here. It is recommended that scrambling is enabled in order to reduce the spurious spectral lines that are produced by periodic data patterns. In ADI devices, scrambling is enabled via a SPI register bit. The default setting has the scrambler disabled. Eight-bit, 10-bit encoding is defined in the IEEE 802.3 Ethernet specification. 8-bit, 10-bit encoding provides sufficient bit transition density, 3 to 8 transitions per 10-bit symbol, to permit clock recovery by the receiver. This encoding also greatly increases the likelihood of detecting single and multiple bit errors during transmission and reception. Due to the nature of the encoding scheme, it provides DC balance of the bit stream and is suitable for AC coupling. The K.28 characters defined in the IEEE spec are used by the JESD204 spec and contain a distinct and easily recognizable bit pattern which assists the receiver in achieving code group synchronization and frame alignment. We will discuss the process of obtaining synchronization and alignment in later slides. So here's the list of K28 characters that are defined in the IEEE Ethernet spec and are used in the JESD204 spec. The K28 control symbols are defined in the IEEE spec, and how these symbols are used and the abbreviation for them is defined in the JESD204B spec. The R symbol indicates the start of a multi-frame. The A symbol is used for lane alignment. The Q symbol is used to indicate when the link configuration parameters are being sent to the receiver. The K symbol is used for code group synchronization, and the F symbol is used for frame alignment. All of these symbols are used during the synchronization and lane alignment process. A subset of these are also used during transmission of sample data in order to monitor alignment. This will be discussed in subsequent slides. Most of our ADCs and all of our DACs include a lane crossbar function between the data link layer and the physical layer. This allows the user to map any logical lane to any physical lane on the ADC output, or vice versa on the DAC input. This could ease any PCB layout restrictions you may have due to pin assignments on the FPGA or a board interconnect. Now that we've briefly described each functional block, let's take a look at the synchronization process. The code group control character, frame alignment character, and multi-frame alignment character are all used during the synchronization process so that the receiver can adjust its JESD204 system clocks and boundaries to properly capture the frame data coming across the link. The lane alignment character that denotes the end of the multi-frame is used to line all lanes in a multiple link. Link establishment through the synchronization process can take place due to a number of events. It will occur upon system reset or power up. It will also occur when the converter transitions to a full operating mode out of an idle mode. Also, the JESD204 receiver can request a synchronization based on errors it has detected. It does this by asserting its sync output. The JESD204 transmitter can also initiate a resynchronization due to a configuration change or a problem by emitting K symbols. Note that in order to avoid confusion, we will denote the JESD204 control characters like K, F, A, etc. by placing a / on either side of the reference. I think it's necessary to do this because there's a lot of K's we're talking about here. Last week we talked about the configuration parameter K. Now we're talking about K.28 symbols, and then which is different from the K control character. So just to avoid the confusion, any JSD control symbol will be denoted with the / on either side of it. Before diving into the details of the synchronization process at the link level, I want to provide some system-level perspective to the process. Depending on the subclass of the system, there may or may not be a higher level of synchronization between the transmitter and receiver. A subclass 0 system has no master timing reference for the link, so the timing relationship of the frame and multi-frame boundaries between the receiver and transmitter are arbitrary. For both Subclass 1 and Subclass 2 JESD204B systems, a higher level of synchronization is achieved using a master timing reference. This ensures a known phase relationship between the transmitter and receiver timing and allows for deterministic latency, which will be covered in a later session. We will focus primarily on Subclass 1 systems in this presentation, so it is important to know under what conditions link synchronization can take place. We mentioned earlier that the link parameters must be set prior to enabling the link and initiating synchronization. In a Subclass 1 system, it is also required to apply the sysref signal prior to enabling the link, but after the parameters have been set. The process for a Subclass 2 system is a bit more complicated, and it is outside the scope of this presentation. At this time, ADI does not support Subclass 2 operation in any of our devices. So once the link has been enabled, and before sample data can be sent across the JESD204 link, synchronization must take place. The first step of the synchronization process is code group synchronization. The CGS phase will initiate automatically once the link is powered on. Remember, before power is applied to the link configuration parameters for both the transmitter and receiver must be set identically and sysref applied. Link power is controlled via SPI-bit in ADI devices using JESD204. The default condition of the link is powered off. Once the link is configured and power enabled, the transmitter will automatically start emitting a stream of K characters. The receiver, for its part, will assert the sync signal low once it has powered up and is ready to receive data. According to the JESD204B specification, the receiver can deassert the sync signal on the subsequent LMFC boundary once it has received at least 4 K characters. In subclass 0 devices, deassertion of sync may occur on a frame boundary. For subclass 1, the CGS phase completes, and ILAS may start only after K generation has occurred for more than 1 frame and 9 octets, and the end of an LMFC period is reached. Some subclass 1 devices, such as the AD9250, may require sync assertion for additional time in order to fully synchronize after the application of the sysref signal. The first character of the ILAS sequence is the R character, which indicates the beginning of a multiframe. Once the receiver detects the K to R character transition, frame, multiframe, and lane alignment begins. At this time, the receiver validates synchronization by verifying the correct sequence of events. So here's a diagram of the initial lane alignment sequence, which lasts for 4 multiframes. Each multiframe begins with a start of multiframe character and ends with an alignment character. The second multiframe contains the Q character right after the start of multiframe character. This indicates that the link configuration parameters are to follow. After the parameters are transmitted during the second multiframe, the rest of the data for that multiframe is a ramp pattern from 0 to 255. In fact, in a subclass 1 system, all data that is not parameter data is a repeating ramp pattern. After the 4th multiframe, as long as no errors are detected at the receiver, the transmitter starts sending sample data. Note that in ADI devices, the length of the ILAS can be programmed to last longer than 4 LMFCs, if so desired. Once synchronization is validated on the receive side, meaning it has not reported any errors, the transmitter begins sending sample data. At this point, if scrambling is enabled, the data will be scrambled. For a JESD204 link with multiple lanes, lane alignment is achieved during the ILAS by each lane buffering data until the last lane is verified. As the ILAS data is received on each lane in the link, it is stored in an elastic buffer until the arrival of the latest lane's R character. So here you see the earliest arriving lane, and the code group sync is transitioning to ILAS, and then the last lane is arriving later. So the elastic buffer is storing this data until this last K to R transition arrives. At that point, the buffers for all lanes are released and all the lanes are aligned. In a subclass 0 system, the latency from the time samples arrive at the JESD204 transmitter input to the time the same sample arrives at the JESD204 receiver input can vary from one power cycle to the next. For many applications, this is not desirable. A subclass 1 system resolves this by adding an additional buffer whose release time is synchronized to the sysref signal instead of the somewhat arbitrary arrival time of the last K to R transition. This feature is called deterministic latency and will be covered in a subsequent session. All right, we touched on resynchronization events on an earlier slide, but I wanted to make sure we addressed the slight difference between this and the initial synchronization event on power up or reset. If resynchronization is initiated by the receiver, it does so by asserting the sync signal low. In this case, the same process as was done for the initial synchronization is followed. Resynchronization initiated by the transmitter is done by transmitting K characters for a minimum of 5 frames and 9 octets. In this case, no response using the sync signal is necessary from the receiver. It simply knows to look for ILAS to begin on the next multiframe. So that's a subtle difference. When the transmitter initiates synchronization, resynchronization, it's a little bit different process. As mentioned earlier, once the ILAS phase is completed without errors being reported by the receiver, the transmitter begins transmitting sample data. During the transmission of sample data, it is necessary to monitor the quality of the link. This is done by monitoring frame and lane alignment as well as error monitoring. Let's take a look at alignment monitoring. Frame, multi-frame, and lane alignment monitoring is achieved through a process called character replacement. This not only allows for monitoring, but also provides a mechanism for correcting any misalignment. Character replacement can be performed on both frame and multi-frame boundaries, or on the frame boundary alone. This is a programmable option selectable via SPI-bit. First, let's take a look at how the transmitter employs character replacement. There are 2 cases that need to be covered: where data is being scrambled and where it's not being scrambled. If data is scrambled, the sample data at the end of the frame is replaced with a frame alignment character if that sample data is the same as the sample data at the end of the previous frame. So if this sample at the end of this frame is identical to the sample data at the end of the previous frame here, then the frame alignment character is inserted into the data stream. Okay? So now, instead of sending the repeated sample data, the transmitter sends the frame alignment character. If the repeated end of frame sample data happens to coincide with the end of the multi-frame, then the sample data is replaced with a multi-frame alignment character. So if the sample at the end of the multi-frame is the same as the sample at the end of the previous frame, the alignment character or multi-frame alignment character is inserted into the data stream. If data is scrambled, instead of looking for repeated characters at the end of the frame, character replacement occurs when a specific code is observed at the end of the frame. If the code OXFC is the data at the end of the frame, it is replaced by the frame alignment character. If OX7C is the data at the end of a multi-frame, it is replaced by the multi-frame alignment character. So, when character replacement is enabled, sample data is being replaced on the transmit side with control characters. On the receive side, the data is buffered and compared to the receiver's octet counter and frame counter. The octet counter sets the frame boundaries, while the frame counter sets the multi-frame boundaries. If a detected frame alignment character is not coincident with the receiver's end of frame boundary, then an error is reported. Likewise, if a detected multi-frame alignment is not coincident with the end of multi-frame boundary, an error is reported. In each case, the sync is asserted low in order to initiate a resynchronization. In order to recover the data that has been replaced on the transmit side, the receiver performs the reverse process. If scrambling is not enabled, when the receiver detects a frame alignment character, it will retrieve the data from the end of the previous frame, which it has buffered, and replace the frame alignment character. When it sees the end of frame or the frame alignment character, it knows that the data that belongs in that slot is the duplicate of the data from the end of the previous frame. Likewise, when it sees the multi-frame alignment character, it knows to get the data that was at the end of the previous frame. Okay. If data is scrambled, the frame alignment character is replaced by OXFC, and the end of multi-frame alignment character is replaced by OX7C. Okay. I hope that makes sense. The JESD204 specification allows for realigning characters or alignment counters on the fly. This is called dynamic realignment. If dynamic realignment is supported, each lane can realign to a or F character without going through the resynchronization process. However, for most applications, this method of recovering alignment is inadequate. This is because the conditions that cause character replacement to occur happen infrequently. Statistically speaking, character replacement will occur once every 256 frames of data for an 8-bit, 10-bit coded data stream. So, if a bit slip occurs that would lead to misalignment, then it may not be detected by the character replacement method for 256 frames or more. That's a lot of potential bad data to be processing without even knowing it. The good news is that these type of errors will be caught by monitoring for 8-bit, 10-bit errors. If the receiver is set up to resynchronize on the event of receiving too many 8-bit, 10-bit errors, the link will recover much sooner than if waiting for alignment characters to reveal the issue. For this reason, ADI devices do not support dynamic character realignment. Instead, the errors are only reported when they occur. So our recommendation is to use the receiver's ability to force resynchronization when too many 8-bit, 10-bit errors occur. In our DAC devices, this is configurable via SPI register settings. Now let's take a look at error reporting. Errors are reported by a JESD204 receiver by using interrupts and also by using the sync signal to communicate back to the transmitter directly. According to the JESD204 spec, there are errors that require resynchronization and errors that do not mandate resynchronization. If the receiver detects an error requiring resynchronization, it will assert the sync signal for at least 5 frames and 9 octets. Errors requiring resynchronization include code group sync error, initial lane alignment error, and too many non-resynchronization errors. The receiver will have SPI registers to set threshold levels for the number of 8-bit, 10-bit errors and other errors. The user can choose to initiate resynchronization when this threshold is surpassed. As we discussed, if the lane or multi-frame alignment characters are detected in a location they do not belong, a resynchronization is required. Errors that do not require resynchronization according to the spec include the 8-bit, 10-bit errors for disparity and not in table. Since 8B, 10B encoding is used, only a subset of all possible 10-bit codes are valid. If a 10-bit code is detected that is not valid, this is referred to as a not in table error. Also, as part of the 8-bit, 10-bit encoding scheme, the difference between the number of ones and zeros in successive 10-bit codes being transmitted is controlled in order to maintain DC balance. This running disparity should never fall outside the bounds of plus or minus 1. If the running disparity, as detected by the receiver, falls outside of this boundary, it is referred to as a disparity error. Another error not requiring resynchronization is unexpected control character. This, of course, does not include the alignment characters, but includes any other control characters in the 8-bit, 10-bit encoding scheme. Okay, so for the errors that don't require resynchronization, the sync is asserted, but it's only asserted for 2 frame clock cycles. So this diagram is taken directly from the JESD204B specification, and it summarizes the link establishment process. In this middle line, we see the sequence of events that starts with code group synchronization, initial alignment sequence, and then the user data portion. Of course, CGS just consists of a stream of K characters. The ILAS lasts for 4 multiframes, with this second multiframe containing the configuration parameters. All other data is ramp 0 to 255 ramp data. And lastly, this is just to indicate that during the transmission of sample data, character replacement will occur. This is a little bit misleading in this diagram because it shows a bunch of control characters being inserted, but in reality, these characters don't get inserted that often. The next few slides on test patterns are similar to what we covered last week during our discussion on the transport layer. I will briefly discuss these again, but will highlight those tests which are most appropriate for testing the data link layer. For the data link layer, the JESD204B specification requires that the transmitter have the capability to output several test patterns. The D21.5 is an alternating 1 and 0 pattern and can be used for measuring random jitter. K characters can be used to measure deterministic jitter. A repeated ILAS can be used to test the transmitter's responsiveness to sync. Either the RPAT or JSPAT pattern can be used to measure different aspects of jitter. JTS-PAT is not required for the transmitter, but is included since it is a requirement for testing the jitter tolerance of the receiver. So the test modes, if you want more detail about the test modes, they are covered in section 5.3.3.8 of the JESD204B spec. As discussed last week, ADCs support many additional test patterns. I won't go into detail here since we covered them last week. Just want to say that PRBS patterns can be used for bit error rate testing, and the ramp pattern can be used to track data through the signal processing chain, and is also useful for verifying alignment between multiple ADCs. You will recognize our block diagram that shows the injection points for the test patterns. If using patterns specified for data link layer testing, you need to disable scrambling and alignment character generation, since they are intended to be input directly to the 8-bit, 10-bit encoder. So those were the first few tests I talked about, the repeating characters and so forth. those were intended to be inserted directly into 8-bit, 10-bit encoder. Since our insertion point is before the scrambler and lane alignment character generation, if you're using those particular patterns, you would need to disable these functions. And you also remember this slide from last week. Our DAC support many of the same tests and similar checkpoints at the transport, data link, and physical layer tests. So again, you would, for the data link test, you would check the patterns at this point. So that way you were checking the data link on both sides of the link. Okay. As discussed with the ADC test patterns, there are mandated tests for link layer testing. Many of these patterns are used to induce jitter. These patterns are used to test the receiver's jitter tolerance. So there are specifications for jitter tolerance in the JESD204B spec, and you can test those doing this. And so we do that when we do the characterization of our DAC product. Many of the patterns can also be used for bit error rate testing by monitoring the link for 8-bit, 10-bit errors. So it's not just PRBS patterns, but also some of these JSPAT and RPAT patterns can also be used for bit error rate testing. I hope that the information here is beneficial to you as you are starting to evaluate the JESD204B interface. Again, if you have any questions that were not answered today or through the presentation, please send them to your local ADI representative or distributor so that it can be routed appropriately. Also, any feedback regarding the content, presentation, or any other aspect of today's session is appreciated. Thanks again. I'll talk to you again next week at the same time. Next week we'll be talking about the physical layer for just a few minutes, but we'll really go more in depth when we talk about signal integrity, equalization, and emphasis.